Consider two sets, x and y. Let's say the elements of the first set are A, B, and C, and the elements of the second set are D and E. We can form ordered pairs by taking the first component of the ordered pair to be an element of X and the second component of the ordered pair to be an element of Y. For example, ordered pair AD is such. Another such ordered pair is AE. These are the only two whose first component is A. Now we can form similar ordered pairs with the first component being B and subsequently with the first component being C. We get altogether 1, 2, 3, 4, 5, 6 elements, and that number actually, which is not difficult to see, comes from multiplying the number of elements in X, which is 3, with the number of elements in Y, which is 2. To see this more clearly, we could draw the following picture, where we put horizontally the elements of X and vertically the elements of Y. Now each ordered pair can be identified by a point in this display where projecting the point vertically down to the horizontal axis gives us the first component of the ordered pair, and projecting it left to the vertical axis gives us the second component. For instance, if this is A, B, and C, and this is D and E, then this ordered pair here is the ordered pair BD, since it projects on the horizontal axis to B and on the vertical axis to D. And of course, this picture is very familiar for those who have seen and worked with Cartesian coordinate system. And then from this picture we can figure it out that the total number of ordered pairs is going to be 3 times 2 in this case, because of the area of a rectangle being obtainable by multiplying the width of the rectangle with the height of the rectangle. So the similar principle as for computing the areas of rectangles can show us that the number of ordered pairs is the number of elements in the first set multiplied by the number of elements in the second set. What we've done here is to form a new set out of two given sets whose number of elements is the product of the numbers of elements of the given sets. In fact, what we've done here is to form what is called the Cartesian product of two sets. The operation of product of sets is what underlies the operation of multiplication of numbers, as this has been illustrated by counting the number of elements in the Cartesian product. So given a set X whose elements are A, B, C, and given a set Y whose elements are D and E, their Cartesian product will be a set whose elements are all possible ordered pairs, where the first component is an element of the first set and the second component is an element of the second set. More generally, we can write out this set as the set of all ordered pairs such that x belongs to x, the small x belongs to x, and the small y is an element of capital Y. So this is the general definition, and what we see here, the blue set, is a specific Cartesian product when x and y are the specific sets displayed by the green and the orange areas. Now it turns out that with all the other axioms of set theory, such as the restricted comprehension and the power set axiom, it is possible to prove that Cartesian product of two sets is also itself a set. So unlike with other constructions, where often we had to require that the constructed set must be a set in an axiom, here we don't have to do it, as it follows from the other axioms. So that's the video on Cartesian products, and of course the importance of this concept goes back to the Cartesian coordinate system that is studied in calculus that can be used to model the universe and many other real-life problems. But also in abstract mathematics, the Cartesian product has many other significances, and in a way it captures the idea of multiplication beyond numbers, generalizing it to sets.